welcome back to my math YouTube channel. In this video, I want to talk about the composition of the trig functions and their inverse functions. Guys, in order to understand that, we have to kind of go back and revisit concepts in functions. So one of the basic concepts that we talk about in functions is the idea of composition of two functions. Guys, I'm not going into a lot of details about how do we compose two functions or more than two functions. I'm just going to write the general definition, and we are simply going to use that definition and apply it to trig functions, because if it works for any functions, it should also work for our nice trig functions as well. So guys, let me quickly remind you the composition. If I have an f of f inverse of x, so if I compose these two functions, guys, if I compose these two functions, the output that I get is just a simple x. But we have to be a little careful here that it does not work out for all the cases. There's few conditions. First of all, f has to be a function. F is a function. So we know how to verify whether a given relationship is a function, and then it has to have an inverse, has an inverse, and we also know how to figure out whether a given function has an inverse. It has to pass the horizontal line test for that. And then, guys, the third one is going to be very important. It is important in context to any algebraic function, but it is very important when we talk about the trig functions. So x belongs to the domain. X has to be in the domain. Maybe I should say x has to be in the domain. X has to be in the domain. X has to be in the domain of f inverse, which is this function right here. So guys, this is something we already know from the functions and the composition of functions concept from algebra or pre-calculus. Guys, same thing works out if I have f inverse of f of x. It is still x, but the conditions, well, it still has to be like something where that f inverse has to be a function and it has to have an inverse, but then there's few other different conditions as well. I'm not so much going to be talking about this one. We'll mostly focus on this guy right here. So it seems kind of that just by looking at this function, and like I'm also trying to think in terms of understanding this, what is actually happening here. It seems like this function and this f inverse is kind of canceling each other out. And guys, that is basically what is happening kind of behind the scenes. And what comes out as the output is just that x, okay? So we can extend that idea to trig functions as well. And that's what we want to do in this section. So guys, from here, we can say that if I have a sine, let us start with the sine function. If I have a sine of a sine inverse x, that is going to be x, but then it has to meet few conditions. So the condition is that x, it is valid for all x's, for all values of x in the domain. Of course, we know that sine has to have, sine is a sine of theta or sine of x is a function. We already know that. And then we know like it has an inverse. We have already talked about that in detail in my previous videos. And then the most important thing is, which we have to watch out for, is that for all x in the domain of sine inverse. Again, I'm just following the same definition that we already know for any function, okay? So for all x in the domain of sine inverse, but we already know the domain of a sine inverse. The domain of sine inverse is between -1 and 1, endpoints are included, right? So that is the definition for calculating the sine of a sine inverse. Guys, same thing we can do for, works for the cosine as well. The cosine of a cosine inverse is also x, and the same thing for x and all. In this case, it has to be in the domain of the cosine inverse. Again, the domain or the cosine inverse, because it's the cosine inverse here. Here we had sine inverse, so that's why I have a sine inverse here. Because you have to be consistent. X has to be in the domain of f inverse. So here f inverse, here sine inverse. In this case, it's going to be cosine inverse. And again, the domain for the cosine inverse, which we should remember, is -1 to 1. We have already talked about the domain and range for the sine inverse, cosine inverse, and tan inverse. And then the third one is, guys, the tangent function. So tangent of the tangent inverse of x obviously is also going to be x, but it has to satisfy a similar type of a condition that for all x in the domain of tan inverse. And the domain of the tan inverse, please go back and make sure you check that. What is the exact domain? The domain for tan inverse is, guys, negative infinity to positive infinity. That means all real numbers. So there are restrictions for sine and cosine, and but there's no restriction, really no restriction for the tangent, because it's the whole number line. So guys, these things are going to be very important when we start simplifying the trig inverse, or the functions which involve trig inverse functions as well. And then guys, keep in mind, we are doing all this finally to kind of help us to solve trig equation. This is all going to come together when we start solving trig equations, because one has to use the idea of the inverses to solve for angles, or to solve basically the trig equation. So guys, keep these things in mind as we move on. So again, like if you want to think in some other terms, it is more like we can think of this as crossing things out. It's like sine and sine inverse are basically just kind of canceling each other, because they are inverses of each other, so they are going to kind of cross each other out. So same thing happens in all these three cases. They're similar functions but inverses of each other, so they kind of cancel each other out, and they give you the x outside as an output. But guys, it is not going to be valid for everything. It has to be in the, like for the first one, x has to be between -1 and 1, because, and it also makes sense that if it is more than that, then we cannot actually find the value, because these things are not going to be defined. Like sine is only defined between -1 and 1. Same thing with cosine. Of course, tangent is defined everywhere on the number line, on the real number line. So guys, this restrictions kind of makes sense if we already understand the basic structure or basic things, or we have basic knowledge of the sine and the cosine and the tangent function. Okay, so guys, that is all I want to talk about in this introduction video. Guys, we can do the same thing if I have a sine inverse of a sine. Again, we'll get x as an output, but then we have to be a little careful with the condition. It has to do more with the range. I'm not really worried about, like, I don't want to really talk about that piece. I think this is going to be good enough for us, because this is the concept that we usually need when we are trying to solve trig equations. So I want to focus on this. But guys, I still want to show you many different types of examples before we actually start doing the solving trig equations. So please take some notes on this. We have to remember a few things, but most of these things are pretty like common sense, and it just comes from understanding the sine function, its inverse function, and understanding the graphs of them, the domain and the range, and all that good stuff. So guys, I will see you in the next video with examples. Till then, take care.